Hello and welcome to our section on proof with quadrilaterals. In this section we're going to be using four-sided shapes to do different types of proofs, and it's very similar to what we were dealing with when we were dealing with triangles. This first example here, I'm going to do it as a two-column proof, and then I will show you how it's done as a flow proof on the next page, just so you can kind of see how they both work together. Alright, so the first thing I do in a two-column proof is I always write down my givens. So I'm going to write down statement 1 that AC is congruent to BC, and I'm actually going to go over and mark it so that AC and BC are the same. That's my reason was given. Step 2, I will write down that AD is congruent to BD. That's also given. You could have done this in one step. You didn't have to write with step 1 and step 2. So AD down here is congruent to BD, and so then we need to figure out, well, what's going to be our next step? Well, our next step is to prove this, figure out how we're going to prove these two triangles congruent. Because if you look, we want to find out that CD bisects angle ACB. So in order to say that it bisects angle ACB, we need to know that ACB can be cut into two same angles. That's what bisect means. Cuts into two, the big thing can be cut into two big angles. Well, if it's cut into two angles, you'll notice that this line CD would be the line that would cut it into two equal angles. So if there's some way that we can show that this angle at the top, that angle ACD, is congruent to angle BCD, if we can show those two angles are congruent to each other, then we can say that this line bisects the big angle, because we have to somehow show that they're the same. So in order to show that they are the same, we basically have to go about showing that this triangle, the triangle on the left here, is congruent to the triangle on the right. And basically what we can do is, if we can show those, then we can use corresponding parts to prove the triangle's congruent, or prove the angle's congruent, which would then get us where we're going. So you'll notice I have these two sides congruent in each triangle. I have a common side that overlaps in between the two, so I could say that CD is congruent to CD, and you could either call this the same segment, they're the same segment in both triangles, or more formally we call it the reflexive property. Whichever one you want to call it, that's fine. And so now I have shown that all three sides in this triangle are congruent to all three sides in the next triangle, which basically means that the triangles are congruent to each other, because if you remember our special property that said if all three sides in one triangle are congruent to all three sides in another triangle, then the two triangles are congruent. So I could say triangle ADC is congruent to triangle BDC. Oops, that's supposed to be put a BDC, and we can say that's congruent because if you notice up above we showed there was two pairs of sides congruent, a pair of sides congruent, a pair of side congruent, so you can see that's how I did it. So down here my reason is side, side, side. And so finally, once I've proven the two triangles congruent, I'm really close here, because remember I said I wanted to show that these two angles were congruent. So now that I know this triangle is the same as that triangle, I can say these two angles are the same by that funny little property that we had the other day. Oops, that's supposed to be 5. We could say that angle ACD would be congruent to angle BCD by that property of corresponding parts of congruent triangles are congruent. Remember, we prove the triangle's congruent, then we can say any part in the triangles are congruent. And that's what the shortcut of corresponding parts, congruent triangles, are congruent. So CP, CTC, the congruent triangle part is the key, and the congruent triangle part is us showing side, side, side. So once we show congruent triangles, then we can say any part that's the same in both triangles will be congruent. That's what CPTC is all about. And so now that I've shown that these two angles are the same, I can go ahead and say what I wanted to prove originally is that CD bisects angle ACB because we know that if we get the same angle on both sides, then by a definition of bisector, then we've bisected an original angle. So by definition, a bisector cuts something in half. Well, we just proved that these two pieces are the same, so something's cutting those angles, a big angle in half, which means the line CD is it. So this is by definition of angle bisector. And so that is a two-column proof of how to do this, and here is a flow proof of the exact same thing. You can see the first thing they did, they wrote down the two given statements, and they went through and said same segments. That's what we just did. We just did that in the previous one. Then they said, after they got all three sides, this was our side, side, side again. There's our three pairs of sides. We can prove the triangle's congruent by side, side, side. Once we've proven the triangle's congruent, we can go ahead and say that the angles are congruent, the top angles that we needed. That's what we were trying to prove. Trying to prove those angles are congruent by the corresponding parts of congruent triangles are congruent. And then finally, we can say, since these two angles are the same, this line, this dotted line, cuts the big angle in half because it cut it in half to make two congruent angles, and that's by definition of angle bisector. These proofs are exactly the same, but they are just written out in different forms, and so these are proofs that we are going to be doing in class. If you have questions about these proofs and anything that we do, please ask.